Rich Edwing, who's in charge of NOAA's Operational Oceanographic Products and Services, or the COOPS program. So Rich has been an employee of NOAA for nearly 40 years, I think. And
45 years, 45 years, yeah.
Goodness gracious. So I don't think there's anything Rich hasn't seen in terms of operational oceanography over that period of time. I've known Rich since I was in Silver Spring about a decade ago, and we worked on a number of projects together. And of course, Rich is well known to Mark Luther. Mark has the Tampa Bay implementation of the COOPS program, and so Rich and Mark work together. So today's seminar is titled Recent Advances in Operational Oceanographic Technology and Products. And with that, Rich, take it away.
Okay, well, thank you. So very much a pleasure to be here, and I very much appreciate the invitation from one center to another to talk today on a topic that I very much enjoy talking about. And I will mention, as I was putting this presentation together and talking about technology, I realized I needed to provide some context for that discussion. So I'm going to really give an overview of COOPS and how we use technology in the 3 observing systems that we manage to, we're an end-to-end program. So we acquire oceanographic information and we turn it into meaningful information for the nation. So let me at this point share my screen. Window, there we go, share. All right, so I'm putting it into, all right, so you can see it in presentation mode?
Yep, that's perfect, Rich.
All right, great. So just a brief outline of the presentation again, brief introduction. I'll walk through our 3 observing systems. I'll talk a little bit about the importance of the continual infusion of new technology into observing systems. And really, infusion of new technology applies to a lot of different enterprises. And we do, R&D and test and evaluation to make that happen. And I'm going to give some examples of how we've been able to improve our observing systems through technology. And then I'll also talk a little bit at the end about how products and services have also been advancing as well, because it's really the products and services that people use. So just some very brief background. My office, COOPS, we're also commonly known as Tides and Currents Office, along with the Office of Coast Survey, which does the nautical charting, and the National Geodetic Survey, which does accurate positioning. Our 3 offices actually go back to the times of Thomas Jefferson in 1807, when the Survey of the Coast was created. And we were created because information was needed to get vessels in, safely and efficiently in and out of seaports. And that was really critical for a young growing nation, and is just as critical to our economy today, that commerce continues to flow through our seaports. So, Coast Survey provides the roadmap, the nautical charts. NGS allows you to position yourself accurately, and my office kind of provides that environmental information that people need to navigate safely and efficiently. So, it is our core mandate. We provide accurate, reliable, and timely, information, primarily physical oceanographic information, but also meteorological as well. We do that through a lot of data and products and services. And in addition to supporting safe and efficient navigation, a lot of our information is really used, is also used for coastal resilience, warning of what's going on when a hurricane approaches, or even out to the long-term sea level trends. We've been doing this for, a couple of 100 years. So over that time, we've built up a lot of very valuable geospatial data sets that describe how the coast has been changing in terms of shoreline, bathymetry, and other things. And that's really valuable information for being able to look forward and plan for more resilient coastal infrastructure and communities. And just at the bottom here, here's an example of an observing system, one of my observing systems. In the middle, we're quality controlling and processing that data. And on the right-hand side, it's one of our products. All right, so one of our 3 observing systems, and this is probably our flagship one, is the National Water Level Observation Network. This is a permanent or long-term network of tide stations. There's 210 around the country, about a quarter of these up in the Great Lakes. We also collect other parameters at these stations, or most of these stations, because it's very cost effective to do so. In addition to these long-term stations, we have about 100 long-term partner water level stations. And then every year there's many short-term stations that go in as well to support, short-term hydrographic surveys, shoreline mapping surveys, habitat restoration projects, things of that nature. On the right, you see just a couple of tide stations. So on the left is this is one of our hurricane hardened stations. We have 10 of these in the Gulf Coast, designed to provide data when most needed, which is when a hurricane's coming through. And on the right-hand side is a kind of maybe a more typical tide station. We put these on other people's piers, and there's a wide range of piers and bulkheads and stuff that we use, and so they can all look very different. Just a few of the products and services that come out of the NLON. Probably the most foundational is, this is a reference network. It helps define the tidal datums along the tidal coast, and then the lake datums up in the Great Lakes. So if you're talking about water levels, that number has to be referenced to something, and it's referenced to these datums. And those datums also determine what are called marine boundaries. And the boundaries are who owns what property along the coast, or who has the authority to extract resources off the seabed. Very obviously, a very complex slide to the right, or a graphic to the right here, which I won't go through, but that's one of the most foundational purposes of the NLON. Another very traditional application is tidal predictions, right? What's the tide going to be doing? We do these based upon astronomics, and a tidal prediction is very accurate on a normal weather day, a kind of an average weather day. But if you have a weather system moving through and winds are blowing, particularly in a bay or estuary, the actual tides can vary pretty dramatically from predicted. And that's why we have real-time data. And so that graphic to the bottom left there, that blue line is the predicted line, and we can predict, tides out for centuries, really. And on the left, you see the red line is the observed, and it's, it's staying pretty close to observed there in this situation. Now, we average our data out over 6 minutes because we're trying to smooth that, that rough surface of the ocean out. But we actually collect that data in 1 minute averages. And that's because the Weather Service needs that higher resolution data for tsunami warnings. And you can just see an example here where, you've got the tide progressing along, and all of a sudden a tsunami strikes, and they're very interested in when that tsunami first hits a location and the amplitude of that signal, because they use that to feed back into their tsunami prediction models, and to make decisions about, and warning folks where to make to conduct evacuations and those sorts of things. So we provide that high resolution data and some specialized tools to the Weather Service for that purpose. Long-term sea level trends. The NLON is the source for sea level trends in the U.S. A typical graph to the right here for Portsmouth, Virginia. You can see there's a lot of variability each year between average sea level. And if you go to our website and you click on any particular station, you get, you see a little box like down here to the left. It gives you some metadata about the history of that record, and then you can go to some of the different products. Those there at the bottom, you can click on those. I mentioned habitat restoration. If you're restoring a wetland, you need to know what the geodetic datum, the land elevations, your geodetic elevations are. You need to know what the tidal datums are, and you need to know what the frequency of inundation of the tides are, the water levels are, because different types of vegetation like different elevations, and to maximize the success of your project, you need to take all that into account in designing it. And then finally, it also helps inform our hydrodynamic models, the forecast out. We forecast out about a week in advance what's going on with the water levels, as well as other parameters. And of course, this data is also used for, research and education and other applications as well. So we operate these stations, from Prudhoe Bay, Alaska, down to Key West, Florida, out to Puerto Rico, all the way out to Guam in the west. So we cover a lot of real estate and a lot of different types of environments. And so, that's where technology helps us overcome some of those challenges. Certainly along the coast, high energy, particularly when there's strong winds, nor'easters, hurricanes, tropical cyclones, tsunamis, and we have to design to to withstand that high energy power that's hitting that tide station every day. Up in the Arctic, Alaska, the Great Lakes, significant ice issues that we have to overcome. In the bottom left, biofouling and corrosion are major issues. You can see some pictures there. So we have to be careful how we mix metals and things of that nature. And of course, biofouling is an issue in warmer waters and colder waters, but it can be a big problem. And then also, just many of the locations we're at are very remote, very limited infrastructure, no power. Just takes days to get there sometimes. So those are things that technology can help overcome as well. So for my program's mission, we're looking to collect long-term, continuous, reliable, very high-quality data to support all the products and services that we do. We really want no gaps in that data, and it's got to be high accuracy and very little uncertainty. We're doing that to standards, right? And so when we design a station, we're building in lots of redundancy into that station. We only go there once a year, and there's been times because of budget cuts or COVID-19 or that we've sometimes not gone to these stations for 2 years, and it's all automated. They keep on operating, but we build a lot of redundancy in there. We have redundant data collection platforms, redundant sensors, and particularly with the water level sensors, we use 2 different technologies because no one sensor is a great solution for everywhere. Selecting the right kind of sensors can offset each other's strengths and weaknesses. Redundant power supplies, communications. And on the land side, we have a benchmark network that we survey the tide station into to preserve the tidal datums. And if that station gets wiped out, we can put it back in, and by connecting back to that benchmark network, we can just kind of pick up where we left off. And of course, when we're selecting a site where we can measure the oceanographic domain that we want to capture. We have to take a look at what's there in terms of local infrastructure, what kind of piers or bulkheads or power and those sorts of things are available, and then what are some of those hostile elements that are there in the environment that we have to deal with. Again, here's some typical NOS stations. Now, on the left-hand side, you'll see this is a Great Lakes station, and the predominant hostile environment up there is the ice, the thick ice that forms in the winter, and it just kind of grinds against the shoreline. So a lot of the techniques we use along the tidal coast don't work. So we have this what's called a sump design. This is a 6-foot diameter concrete sump that goes far enough down to the ground so that we can run a 1-foot diameter intake pipe out into the lake, far enough so it's kind of past that, and low enough so it's underneath that grinding action of the ice. And then we can measure using a float-driven device inside that sump. Again, to the right, the far right, just a couple of different kind of piers that we put gauges on, and again, our offshore gauges in the Gulf Coast that we designed. These were designed right after Katrina and Rita and deployed. There's up to 10 of them now. We're doing an 11th right now off of Dolphin Island in Alabama. But these have all survived and provided data very successfully through all the hurricanes that have happened since Katrina and Rita. All right, so I've talked about the sensor technology. For our coastal stations, we had been using, since the mid-'80s, this acoustic device. And this is a sound device. It just sends a pulse of sound. If you look at that little schematic down there in the lower left, you can see there's what's called a sounding tube. It just sends that pulse down that sounding tube. It just measures the time it takes to get back. But that design, it has to be protected by a protective well, because that half-inch tube isn't going to survive in the environment. And then we have to do some things at the bottom with what we call parallel plates to reduce Bernoulli effect, drawdown effect from currents. And of course, all of this can biofoul and corrode and those sorts of things. We have temperature sensors inside the well, because sometimes we have to make corrections for temperature change if there's a temperature gradient over that well. So there's a lot going on with that design. And that's why, if you look over to the right a little bit, you'll see the radar, the microwave gauge. This is what we're transitioning over to, and we've converted about half the network to this, because even though the sensor itself is about the same cost, roughly $2,500, $3,000, we can get rid of all of this, these components that are in the water. That's just less cost, It also gets rid of the biofouling issues, the corrosion issues, the temperature issues. We don't have to send divers in the water to maintain. So anytime with technology infusion, if you can reduce costs and improve accuracy, reliability, those sorts of things, that's kind of a win-win. Now in the center there, you see the shaft angle encoder, and again, I mentioned we use a float device in the Great Lakes. We have a couple of them for backup, but just as those floats go up and down, they turn these shafts, and they just count. They very accurately count that motion and record it and send it back to us. Now on the right-hand side, at most of our coastal stations, we use a pressure sensor, a relatively inexpensive pressure sensor as backup. Now we put that pressure sensor inside the data collection platform, which you can kind of see in the upper right photo, and it's kind of in the upper right part of that box. And we just bubble air down through this to this orifice, this brass orifice, which is somewhat biofouling resistant. And we're just monitoring the change in the pressure, the hydrostatic pressure over that orifice, and recording that data. And that's there to kind of, if the primary sensor fails, it helps fill in that gap. And sometimes when storms come along and they're driving that water level, storm surge driving that water level really high, if it gets too close to either the acoustic or the radar, they kind of have what's called a blanking zone. There's a kind of a couple of feet below the sensor where it really can't measure. If it gets up into there, we lose the measurement. But the pressure sensor, which is kind of looking up, if you will, still continues to record. So that was a quick run through of the water level observation network. Then we have our currents observation program, but there's no permanent current meters with this program. We are going around and we are doing short-term deployment to current meters. Most of them just 30 days, a lunar cycle. Some of them will be longer, 60 to 90 days is kind of more of a reference station. But we're doing that to really update tidal current predictions. We have about 3,000 locations around the United States where we put out tidal current predictions. And actually, we do this about the same amount of locations for the tides as well. The most common way we deploy current meters is through this current bottom mount sort of approach here. You see that on the right. And again, the main product out of this program is those tidal current predictions, although it does also help inform our hydrodynamic models as well. So they have their own set of environmental challenges. You can see to the left here, in some places, you can have what's called sand waves. These are kind of underwater dunes, and they can migrate pretty rapidly, and they can be pretty high and migrate pretty rapidly sometimes. And sometimes we put a bottom mount down there, it gets buried, and we can have a hard time finding it and retrieving it. Same thing with mud. Not every place has a nice sandy bottom or hard bottom where those bottom mounts rest nicely on. Sometimes they just go down into this mud and just kind of keep on sinking. And it can be hard to retrieve those as well. And then, of course, biofouling is an issue with them as well. It's just amazing how much stuff can grow in a month's time on some of these devices. And on top of that, it's not really an environmental factor, at least a natural environmental factor, but vessels coming by with these bottom mounts, and if you're dragging fishing nets or anchor lines or things of that nature, they can snag them and cause problems. And with some other types, which I'll show you in a minute, we can have vandalism. So we do these current surveys, a few locations around the country each year. We pick locations where we haven't been to a long time, or maybe people are telling us our existing predictions are off. They've gotten out of date because it changes over time. It's really kind of a 5-year process from the time we make the decision to go to a location, to plan it, to go out and do a field recon, to talk to people, to find out where's the best place to put these devices, and then actually deploying them and bringing the data back and processing it and getting the data out. Here's just where we've been the last few years. Some of them are multi-year. Some locations are multi-year surveys just because of the size. You can see we put a lot of deployments out. And I think I'm not aware of any other entity out there, whether it's government or private sector or academia, that kind of does this to the scale that we do this to. So we have a lot of expertise in this area. So unlike the water level network, we really have one kind of workhorse instrument that we use for our surveys, and that's the acoustic Doppler current profiler. And really, that's it's sending out a pulse, and it's looking at particles that are, moving in the water column, and then looking at, the frequency shift of that reflected particle, if you will. And this illustration to the left, this is a bottom mount looking up. And we can measure and kind of put into bins the current speed at different depths, because the current speed isn't uniform all the way up to the water column. And we've also developed ways to mount these things sideways, so you can look across the channel. We can use this in places where we're maybe up a river a ways, and you can see across the whole channel, and you really can't put other things out there because there's too many vessels or things going on. And again, to the right, here's a bottom mount. But a lot of the technology development we do is really kind of how to deploy these things. We're really not developing the instrument itself. We're other people have done that. It's kind of how do we deploy it. So a number of ways that we deploy it. And some of these ways were developed for the port system and have come back to the currents program. But here's the bottom mounts, and just different kind of platform designs. You can see they all are sloped in some way. So hopefully if a fishing net or an anchor line or something kind of passes over it, it's just going to kind of go right over it and keep on going and leave that bottom mount alone. We kind of drop these down, and we have acoustic releases and buoys and stuff. So when it comes time to pick these back up, we trigger the release, and the buoy and the lift ring come back up to the surface, and we can snag them and pull them back up. That could be interesting and challenging finding these sometimes, and also getting them back up. But we have a high recovery rate, and it always wasn't that way. And that's because a lot of research and development was done on these mooring systems and recovery systems and the bottom mounts and so forth. So when it gets too deep for a bottom mount, we deploy these what's called subsurface buoys, where we kind of have an anchor at the bottom, and this buoy kind of floats up to some depth, and we're measuring that water depth above it. We're really interested in that top 50, 60 feet of the water column, because that's where those big commercial vessels, are transiting, and the currents are pushing against their hulls. Again, there's just different types of buoy designs depending on the current strengths we know we're going to be facing, and those sorts of things. Now, again, here's something that we developed for the port system, because this is a way to put current meters out on buoys, Coast Guard buoys, to get the measurements right where the big commercial vessels needed them, right there at the edge of the channel. If you look at that lower left illustration, we designed what we call a clamperatus, right? It's we can just bring this whole thing out there and kind of drop it right on the buoy. And that's because the Coast Guard, fortunately, uses the same designs for all their buoys. The buoys can vary in size depending upon the ocean conditions, but they're all designed the same. So we can we've designed this clamperatus to drop down to some of these lifting hooks and clamp right on there. But it's just got the electronics on top. In the ADC piece, it's right at the top of that small tube that you see, and takes the measurements. And you can see some folks on these buoys, mounting these things up. And then there's an interesting calibration sort of procedure where you have to tie a line to the buoy, and there's somebody sitting on there with a laptop and a device that's got a compass in there, and we kind of have to spin the buoy around to calibrate it with respect to direction. And again, something else that we developed for the ports program is a side looker. As I mentioned earlier, it can look sideways, but we also use it now sometimes for the short-term surveys. And again, but when these things are mounted, particularly permanently, long-term for the ports program, we have to be able to there's some sort of channel or a way that we can kind of lift these things up and down so that we can service them, so we can, clean them off occasionally if it's an area with high biofouling. All right. So the water level network and the currents observation program, that's the tides and currents, that's our basic tides and currents program. But that gave us the expertise to develop something called the ports program, and we're actually celebrating our 30th anniversary of the start of this program. And the very first one was in Tampa Bay. And that's because some of you may recall there was a very serious accident back there in the 80s. Where a vessel ran into the Sunshine Skyway Bridge, and there was loss of life. And the investigation reports that came out said, hey, they had real-time data, and they had data from multiple sources or multiple types of data. They may have been able to avoid this accident. And so NOAA was kind of tasked to develop a system to do that, and we did so. And at the time, it was very unique because it provided real-time data, but it also integrated data into products that pulled all that information together. So you didn't have to go different places to get, this type of data or that type of data. Those sorts of features are no longer unique, but the port system has continued to evolve and grow over time. So the way it works, if a local area, maritime community says, hey, no, we need more water level stations. We need permanent current meters. We need more meteorological stations, et cetera. And they partner with us. They actually fund the establishment of that local observing network. And then we bring the data in and we quality control it in real time to make sure it's good. And then we put that data back out through products and services. And so over time, here's all the parameters that we can provide through the ports program. It didn't start off with all these, but as people talked to us and said they need these different parameters, we found a technology that could provide them. Some of the newer measurements or visibility is to the visibility sensor over to the left here, air gap, a bridge clearance sensor, which is kind of an example here in the middle, because the ships have continued to get larger and larger and larger. They've always had grounding issues, but then they started striking the bridges themselves, which were built many years ago. And we developed something called an air gap sensor, which lets them know they have enough clearance to make it or not. And I won't go through all these parameters here. I will mention that we do partner with the Corps of Engineers, and we were talking about this just a little bit earlier, through the Coastal Data Information Program to provide wave information through ports. And also we work with some of the IOS regional associations to bring in high frequency radar data for ports as well. Most of the IOS HFRs are open coast and looking out, so it's really just the ones that are inside some of the estuaries that are of interest to us, and there's not too many of those yet, but IOS is working on it. We've got these capital port systems in over 35 locations, and one uppercase port system can service more than one lowercase seaport. And right now, where we're at, over 90% of cargo transits these top 80 seaports, whether you measure it by tonnage or value or other ways. So we're really covering, most of the cargo that comes in and out of the U.S. right now with these systems, and they have been demonstrated to reduce accidents and improve efficiency. Okay, so that was a quick run through the three main observing systems that my program operates. But as I said, it is essential to continually, infuse new technology into those systems to keep them current, to keep them cost effective, to keep them, constantly meeting people's needs. This is just some pictures from, I have a facility in Chesapeake, Virginia, where we conduct a lot of our field operations out of. Just kind of a test track to the left there. In the middle, that's our kind of antenna farm where we test a lot of things. It's off to the side of the building. To the right, just some tanks inside where we can vary the water level and work with sensors. We have access to vessels. We can go out and throw stuff in the water to test. Bottom center, this was kind of a very kind of simple, low-cost high gauge we were developing, and just a buoy there to the lower right. I won't go through this, but I will emphasize we really don't do much research and development in terms of observing technology. We're really looking to leverage R&D, and actually very mature R&D that other people have done. We're always keeping an eye on what's going out there in industry and academia to see what's ready to be able to, what's mature enough to be able to transition into our observing systems to improve them. But that's still a pretty complex process because a lot of test and evaluation has to be done to make that happen. But again, the goal is always to reduce costs while improving things in some form or fashion. And I have a small part of my program which people dedicated to doing just that. And in the backside of their building, this is just a big platform where they can add all sorts of sensors, and there's some larger tanks down there. You can see they can vary water levels and do a lot of testing. You see some ADCP bottom mounts kind of stacked there behind it. But also I should mention, we do a lot of calibration, sensor calibration. Some sensors need to be calibrated every so often to make sure they're still measuring what you think they're measuring. That image, the picture on the left and that kind of graphic on the bottom, I'm not going to go into much detail on that, but we would calibrate these acoustic sensors, and both any kind of electronic sensor, water level sensor, acoustic, acoustic or radar, they have an internal zero, which it starts measuring from. And we need to know where that internal zero is, and we need to transfer it kind of outside of the sensor to a survey point, so we can survey from that sensor to that land-based benchmark network. So we know where to start our measurements from and to monitor the stability of that sensor. So in that kind of the center, those kind of big steel, aluminum, whatever they are, frames, that's where we kind of determine the offsets for the radars. And off to the right, this is a pretty large calibration facility we have. It's still in the back of that building, but if you look in that one photograph, you can see where we can mount a microwave on that frame. It's got that large target to the left, and that kind of moves up and down those railroad tracks. And then we have a small instrument shelter there that has all the automated computers and stuff that kind of move that target back and forth, and and monitor the sensor to make sure it's tracking that sled properly. And as far as I know, we are the only facility in the U.S. that does this type of work. I know there's one in Australia that does something very, very similar, but we're the only one in the U.S. So now I'm going to move on to network enhancements. And again, the primary water level sensor for our NLON is very important to us. We are very conservative and cautious when we make a change. And again, I've already talked about a lot of this slide. Here's again the graphic of the acoustic sensor to the left. I've already kind of talked about the cons of that, if you will, and then the advantages of moving over to the radar. It truly doesn't contact the water. We get rid of all that kind of those in the water components to the left. We still have a mounting frame we have to put it on, but that costs less. And it's not in the water, so we don't have to worry about corrosion and biofouling and divers and those sorts of things. We have found that these radars, they don't drift very much. A lot of these have gone 5 years or more without needing any adjustment. And again, we don't have that temperature dependence. So there's one of our Sentinel stations in the middle. You can see to the right, there's that Aquatrack, protected wall going down. You can see the large brackets, a lot of stuff there to take care of, and you probably can't even make it out on the left-hand side, but there's a microwave there, and easy peasy. It's just looking down to the water and measuring that. But again, very, very conservative and slow in how we make these changes. So when we first, started looking at the radar, we, came up with an evaluation plan, and then we did a lot of test and evaluation so we could understand it, and, particularly in how to set it up and use it. And that helped, lead to instructions to our field people. How do you design this thing? How do you operate it? And that allowed it to go into operations. But even after that, we kept doing additional analysis. Well, how does this behave in super high energy environments, et cetera? But we certainly, I will say, we did more testing on this than anyone else in the world. And that helped inform this IOC manual on radar gauges. I will say we took longer to transition over because a lot of countries went to the radar because it was just a very inexpensive technology. It had a lot of very obvious, advantages, but some of them ran into trouble because they found out later there was some systemic issues in the sensors they selected that were degrading their data, and they weren't really aware of it. And we were able to avoid that whole issue. Having said that, we're also now looking to dual purpose these radar gauges, not just measure water levels, but to measure waves and put out wave products with these, because these things are continuously sampling the water. And as I said, we average over 1 minute and 6 minute intervals because for our water level products, we're interested in that nice kind of smooth tide curve, if you will. But we can also start to put out wave products, not direction, but amplitude and period. because there's a real lack of very near shore wave measurements in the U.S. and probably in most countries. You have the far offshore NDBC network that measures waves. You've got the near shore, Corps of Engineers network that measures waves, but there are very few measurements right along the shore, and there's a real deep and gap for that information. So, and that's again, we're not having to put out new hardware. We're just really kind of leveraging stuff we already have in place. We also developed a way, and again, well, other people have done this as well, but we can put, a GNSS sensor on a buoy and put it out there to get measurements, short-term measurements in areas where maybe we can't put in a short base station, particularly up in Alaska, a lot of remote areas, no power, very rocky coasts or high energy, but for short-term hydrographic surveys or other uses, this buoy can do the trick. And you'll see GNSS coming up again and again. This is a technology we're now starting to co-locate with our water level network for multiple reasons. We're looking to, and if you look, you can see on some of these illustrations, we're trying to integrate it directly with the mounting platform for the water level sensor, because we can use it to also, to monitor the stability of that water level sensor. It also puts the measurements directly into that space-based, GPS reference frame to the ellipsoid, referencing it to the ellipsoid. And also it helps us with measuring what's going on with land motion. Our tide gauges have the sea level trends, and those are relative sea level trends. In other words, they're integrating what's going on at the coast in terms of land motion, global sea level change, and any ocean dynamics, regional ocean dynamics that are going on in the area. But when you integrate these two technologies, you can parse those things out. And that sensor also offers some promise as perhaps a next generation water level measurement system. Again, other people have been doing kind of R&D on this, and you can kind of see this title down below, the accidental tide gauge. GPS antennas are directly receiving GPS signals or GNSS signals to position themselves, but those signals are reflecting off of other things, and people have found a way, developed methodologies of using that to monitor, water level as well. And we've now gotten engaged with that community to start testing and evaluating whether this can meet our requirements as well. At this point, it's probably not yet, and this is just a sample or an example, I should say, from where some testing has been going on in the Great Lakes by Ohio State. But that dark black line is our lake gauge. That blue line, or the blue line, is the GPS signals, and you can see there's a lot more variability there with the GPS signals. Too much variability for what we can use, but people can work on that. And over to the right, that interesting kind of barcode, almost look graphic. It's showing outages in GPS signals, which can create gaps in the data as well, which is not good for us. But these are issues that can be worked on. And, GPS tide gauge has a lot of promise, particularly for remote areas, because low energy, low power requirements. You don't have to mount it right over the water necessarily. So a lot of advantages for that technology. Okay, so current meters. Again, most of what we've worked with current meters on, the community, the larger community is working on improving the ADCPs, and there's different manufacturers and different models that we use, and we take advantage of those improvements. Most of our work's been on how to deploy those things out there. Again, here's just some of the different deployment methods down there. And once you innovate something, you're not done. I mentioned a number of years ago, a couple decades ago, we developed a way to put these ADCPs out in Coast Guard buoys and bring that data back, because that's where people really needed it. But we had to do it through a shore station. We had we couldn't get much of the data collection platform and other things out there. It just took up too much room, and so we kind of had to minimize the electronics offshore, and we just kind of use a radio link to bring that data back to a shore station, which we could then use a data logger to process it further and format it for transmission back to us through our GOES satellite. But more recently, we've been able to really improve that system by getting rid of that shore station using an iridium satellite to bring the data back directly from the buoy, but also being able to miniaturize and get all the data logger and other things out there on the buoy. So to me, this is like one of the best examples of infusing new technology, reducing cost, improving the reliability of that of this system, because we lost that radio link would drop out a lot, and we weren't getting the data reliability we wanted. The satellite really has improved that, and now we can put these things farther off. This is what allowed us to establish the Miami port system, because they wanted data on buoys further offshore than the radio link could support, but with the iridium we could get them out there. So a lot of significant improvements there. I mentioned it's just not about the ADCP, but it's these mooring systems. This is a system we've been developing, testing, and evaluating for very deep deployments, 300 meters. You have to pay a lot of attention to what goes on with these long, these long cables, because as they start building up vibration, and particularly in high energy environments, current energy, it can cause problems. So there's all these parts and pieces you have to understand how they interact with each other, to be able to make sure you're putting stuff out there that's going to work and be recoverable. Another example is where we developed a kind of a quickly deployable real-time current meters system called Kirby. My engineers aren't very good at acronyms. It kind of somehow stands for real-time current meters on a buoy. Kind of make that work. But this gets deployed when there's an oil spill or something else bad goes in the water, and the Coast Guard and others are running trajectory models to figure out where that oil is going, when it's going to get there, those sorts of things. We had to integrate a tilt sensor with this, because this thing's obviously bobbing back and forth to take those error sources out of the measurements. And now kind of getting to some other types of sensors, mainly for the port system. Again, I mentioned we developed this air gap, this bridge clearance capability. Now, we did this back in 2005, and we used it, at the time, it was a continuous waveform radar. You can see that kind of green, kind of that center top photo there. That was a Miro sensor from Norway, cost $30,000, very high power requirements, but did the job. But over time, we've been able now to move to the same sensors we're really using for our water level measurements. It's a much lower power, it's a pulse radar, and these things cost about $3,000. So $3,000, versus $30,000, that's a factor of 10, cost reduction. And there are places now where we've gotten panic calls because there's a new larger vessel coming in, and they know it's going to be a very tight fit under a bridge, and the Port Authority will not allow that vessel in unless there's a NOAA air gap or port's air gap sensor on that bridge. And so this has become, a hard requirement for many places where you've got this issue of a bridge that was built a long time ago, and vessels have gotten bigger, and people were worried about getting them in safely. Another example where with the fog, people wanted fog measurements, and we did a lot of test and evaluation of existing visibility systems with the FAA and Coast Guard, and we found this one to the left here, which really was best suited for the marine environment, but it's got high power requirements, it's fairly expensive, and it's just a point measurement that you can extrapolate out from, but it's still just a point measurement. And actually, this is a case where we did fund some R&D, where NOAA has a program called the Small Business Innovation Research Grant, and we put out a requirement for somebody to develop a better fog sensor, which is pretty far along now, where somebody using multispectral imagery can look, use this to measure fog, rain, visibility out over quite a distance, and make statements about that. And it's a much less expensive technology, and it improves the accuracy and it improves a lot of what this other sensor can do. So again, you're never done. Nothing ever is done in terms of evolving technology. So the last just piece of technology I'll talk about is we are also looking at wind power to supplement our solar, battery, and AC/DC, power sources for our stations. Because particularly in some cases, solar power doesn't work very well, where there's a lot of clouds or like up in Alaska where you don't have a lot of sunshine most of the year, and just some pictures of a wind propeller type system and a turbine type system. So we're almost to the end here. I'm going to say a few things about products and services. Observing systems are very cool technology, and we love getting out there and working with them, but it's really what comes out of them that counts, because people are using that to make decisions, important decisions, and often those are safety of life and property decisions. And it's not just getting the data out there, through products, but people have to, it's got to be easy for them to find, it's got to be easy for them to access, and it's got to be easy for them to understand if those things are going to be effective. So I'm using our ports graphics as kind of an example of static graphics, and we're still using these today because they still meet those users' needs. And people receive information differently. Some people like numbers, and you can just see that information in the middle there. Some people like graphics, but the point is these are not really interactive. They're providing a snapshot of what's going on right now, and it's providing multiple types of parameters. And that's what pilots on a ship vessel need. They're up on the bridge of the ship. They're making decisions, lots of decisions. You have to take in lots of information, and they need to look at stuff and just see it as a snapshot. So they don't want anything that's interactive. It needs to refresh and update, but they don't want to have to play around with things. So this still works for them. But for most other people, we've gone to a much more interactive approach. And again, we've done a lot of surveys and things that tell us how people like to receive information. If you go to a website, you see a big map of the U.S. You can kind of drill down, Tampa Bay. But if you drill down, you see these pins, and they kind of tell you what kind of sensors are there. If you click on the pin, a box comes up to the right, and this is water level, so it tells you what the tide predictions are for today, and it tells you what the most recent information is from the sensors that are there. And you can toggle, between metric and English units and other things. If you click on this little plot data box, that's kind of in the lower left hand of that upper right graphic, you'll get plots of these different kinds of data. And this allows you to kind of go back and forth through time. You can scroll over the observed and prediction lines with your mouse, and it's going to give you the exact values of each 6-minute value. You can, I think, toggle what datums you want. So lots of interaction, lots of options for you to use. Now, the navigation community likes their data referenced to mean low water because they're looking for a conservative estimate of the water level. But the emergency response inundation community, they like mean high water because that's where coastal flooding can start happening. So through our coastal inundation dashboard, we reference all of the data to mean high water. And this is our dashboard. And this is taking advantage, obviously, of GIS and geospatial, orientation and capabilities that it offers. And all of these, these blue pins are our water level stations or partner water level stations. As a storm approaches, pins that are starting to near flooding thresholds start to ping, let you know something's going on there. And you can just pull all sorts of information, into this tool. And when when a storm approaches, we get, our hits go through the roof on this tool. But if you click on one of these pins, you see a graphic kind of similar to the left, and we worked with the Weather Service to define kind of, minor flooding, moderate flooding, and major flooding kind of levels for each station. So you can, you can get some information about that as well. With some of our other types of products, I talked about the long-term sea level trends and other types of long-term, tools like extreme water level to the left there. After some of our major storms, we would do kind of a special report. Again, very static, non-interactive. And I can't really, demonstrate this particular tool, but we're doing the same thing now where you click on one of these arrows and lots of other information comes up. But you will see this little graphic down here. Let me go to the next slide. We can do things like these animated data visualizations. And I really love these. For sea level, each time a blue line every time a line goes across the screen, that's monthly means over a whole year. And you can see the years kind of ticking off here. But as time goes on, you can see that sea level is kind of slowly rising, right? Although there's a lot of variability, So, it kind of helps get across a lot of points at once that kind of a static graph maybe can't necessarily do. And over to the right, you have this kind of cool visualization of a tsunami that was generated. And as it hit different tide stations at different times, you can see the tsunami signal generate and then kind of settle down after a while. But it kind of gives you a better kind of overall view of what's going on. So last slide. And now we're also looking at, integrating real-time and model forecasts. This is what we're trying to do with some currents. Each one of these little arrows is a current vector. You can click on them. You can get kind of depths with forecasts of what's going on at depths. You can go back and forth in time. Lots of information on here. Maybe too much information on here for some people, but it just kind of shows you the power of what the tools can do. And again, it's technology evolving and allowing us to make things better. So with that, I will stop and left a little bit of time here for questions. I apologize. So let me stop sharing.
Well, thanks very much, Rich. Excellent presentation and a lot of information about what your group does. Really valuable things. We have some time for questions, so if people want to either use the raise hand feature in Teams, or if you can just shout out your question too. So, well, go ahead. So I'll start if you don't mind.
Nope, go ahead.
So Rich, you showed a bunch of these long-term data series that go back to the 40s and even earlier in terms of sea level measurements. And so obviously the technology you had in the 40s, the 30s, the 20s is a lot different than now. So how do you assure intercalibration of the instruments so that you're actually not reading more precision or a bias in these modern methods versus, I guess, a ruler taped to a mirror?
Yeah. So, around the 1840s is when kind of the first automation occurred, right? Before that, it was tide staffs, people going out and reading a graduated board, in the water, at whatever frequency they could do that at. And obviously, if you had a highly variable surface, that could be hard to do. But in the 1840s is when there was the first automation of a float going up and down in the well and kind of drawing a trace on a piece of paper. But again, we would also at the time have a tide staff in and make people reading on that tide staff and survey that in and kind of put as much quality control on that technology as we could. And as you mentioned, over time, as technology and accuracy has improved, we've continued to improve the accuracy. And people have actually gone back and by rescuing data, doing data rescues of these old readings and stuff, they've been able to kind of reconstruct sea level trends going back even further in time to get a longer history. But really, for us, those long-term sea level trends started in the 1840s. But we're always and that's why I said we're very, very conservative when we make a change to that primary water level sensor, because we don't want to introduce any sort of systemic error that may be there.
So do you basically run these in tandem for a while and basically?
Yes. Yeah, we do long-term comparisons. Before we even deploy the new technology, we do at least 3 or 4 years of just overlap comparisons, and then we still do 10-year comparisons even after we've made the decision to go into operations, because you can still have issues arise. And I will say with this radar technology, something we learned afterwards was in really high energy in these hurricanes, when it's coming in, like Hurricane Harvey was a good example. When that hurricane came in and basically was blowing water horizontally, right? The radar gauges could not measure water levels anymore, but the pressure sensors we had did. So that's always, the power of using two different technologies. Two different types of sensor technologies, because no one type of sensor works well everywhere.
Sarah, your question?
So I'm Sarah today. You had so many examples of these amazing products, these incredible time series that you have. And originally, these sites were installed for safe navigation. Have the considerations upon site selection, have those changed as maybe research questions have gone into considerations, or coastal concerns have kind of evolved?
Yeah, so for the water level network, we've actually done what's called a gaps analysis for because we were always getting asked, well, how many stations do you need, right? And we really constrained it to that fundamental foundational purpose of providing a vertical control for determining tidal datums, right? And if you do that, each tide station kind of has a span of control, kind of depends upon the coastline and bathymetry and other things, but you can extrapolate those measurements out, the tidal data out a certain distance. And, so we could do that for their existing stations, and we could show there were gaps in between, right? Now, most of our existing end-launch stations were sited mainly in seaports and places where there was a lot of commerce, right? And so now most of our gaps are in areas where maybe there's not as much commerce going on, but you may have a lot of coastal communities, and that, and so it's more of a priority than an approach, if you will. And now we're looking to fill some of those gaps to get people those long-term data records they need for those resilience products. And of course, there's areas like Alaska, which has a lot of gaps, just because most of our gaps are up in Alaska, just because it's been so remote, and up until relatively recently, very little activity or need for measurements. But of course, that's changing with the retreat of the ice up there, and we're trying to get up there and do more measurements. But that's actually still very challenging because of the ice conditions and the remoteness and all those sorts of things. So we haven't come up with it. That's where I'm hoping the GNSS Center really proves out, because that could be a really great solution for up there.
Thank you.
Yange?
Hi. It's nice, very nice talk.
Thank you.
I know the ocean circulation model, coastal ocean circulation model, and tsunami models are operational in NOAA co-ops.
Right.
So I'm wondering, is there any tsunami model in the Gulf of Mexico? I know tsunami is not a big threat as for the U.S. West Coast. I know there's a coastal ocean circulation model is operational on the for the Western Gulf of Mexico, but not one for the Eastern Gulf of Mexico yet. So I'm wondering, is there a tsunami model for the Gulf region?
So I believe there is. So first of all, my office, we operate the hydrodynamic models along the coast. And you're right, we haven't fully built out coverage around the U.S. We're getting there, but and you're right, we have it from kind of the Texas border almost all the way around, but we don't yet have the west coast of Florida filled in. We're working on that. And I will say, prior to the Indian Ocean tsunami, really only the west coast part and the Pacific Island part of our network provided high resolution data to the Weather Service, because that was the high risk area, right? But after the Indian Ocean, we put in this 1 minute data capability everywhere. So now the network provides the information needed everywhere. Great Lakes, it doesn't matter, but along the entire U.S. coast. But the Weather Service really operates those tsunami models, and I don't know what their coverage is. I suspect they have the ability to do it for the Gulf Coast and the East Coast, because they were told they needed to do that after the Indian Ocean event. But I don't have specific knowledge.
Okay.
Any other questions for Rich? So what I would say, Rich, is we'd love to have you come down, sometime when everybody's moving around the planet again. And, we have a lot of mapping related things that we want to do in Tampa Bay, and it would fit right in, I think, with some experimental work on some of the observations, including the ADCP work and the upgrading of the tidal gauge measurements that Mark is going to do as well.
Yeah. Yeah, no, that would be great. And I'm certainly excited. You guys are a new center, and we're I think there's a lot of things we can do together. We just need to figure out what those are, and take advantage of each other. So,
if it's possible, could I still ask a question?
Absolutely, Dave.
Sure.
Yeah, speaking of Mark Luther and the Skyway Bridge, we've noted that many of the ADCPs on occasion will be covered up by the sediments that are flowing through.
Right.
And so you've got this dilemma of trying to monitor something that's getting covered up.
Yeah.
Any ideas on solutions to deal with that?
Yeah, well, you're identifying some of those environmental challenges and that we have, and biofouling, getting covered up, those are constant issues. And really, you just have to have the ability to go out. You monitor those. The first step is to monitor that information so you know that's happening, and be able to understand, make a good guess that's why it's happening, and then being able to go out and deal with that. Now, you could also look at, if that's a constant issue with a bottom mount, maybe there's a buoy solution, or maybe there's something else that will work better. You can look at one of these other, deployment methods that we've come up with. Or, if there's a buoy, particularly the Coast Guard buoys, if there's a Coast Guard buoy nearby, converting over to one of those might be a better solution.
Our solution at the Skyway is that we have 2 bottom mounts, and they're spaced about a half a wavelength of these sand waves apart. So when one gets buried, we just switch over to the other one and use it.
Yeah, there you go.
Thank you.
Either that, or we need some kind of crawler that will, constantly.
Right.
Yeah, I mean, as we all know, it's a very challenging environment to operate in, right? And particularly when you're trying to do it reliably and, keeping that data, that information coming. I'm waiting for someone to come up with a good salinity sensor that doesn't have to be cleaned every other week, because of the biofouling and issues. Again, I don't really do that kind of R&D. Other people do that. We're there. We're waiting for that to happen so we can leverage that.
Well, it's so important for things like the vertical sound propagation, for a lot of the acoustic instruments as well.
Right. Yep. Yep.
Well,
Right.
And
Okay, go ahead.
before we go, we're planning a small party down here, probably in September, to celebrate the 30th anniversary of Tampa Bay ports. I'll fill you in when we have an actual date. We'd love for you to come down here if you could.
Okay, that would be great. I would certainly like to. I'll have to see if we're allowed to travel yet for those sorts of things, but we'll just have to see. But
That's why we're hoping by September you will. So
yeah, I hope so. Yeah. So all right. Well, if there are any follow-up questions, that I can't stay online and answer, I'll just send them to Cheryl/Sarah, and I'll be happy to respond later.
Appreciate that. Well, everybody give a clap to
Thank you, Rich.
thank you, Rich.
Okay. Thank you, and bye-bye, everyone.
Last thing I'd like to say is that our next seminar will be on July 28th, and it'll be Colleen Peters from Sail Drone who will be giving us a talk. So thank you all very much for participating. Take care.
Bye.